All right. We are up. We are live. Audio and video is up. Welcome back to Statics. I wanted to run something by you. If you go to the class schedule, it looks like there was an exam coming up. If you recall, actually, I'll tell you what, let me pull the class schedule up. I think that's worthwhile. So that everybody's aware of what I'm doing and why I'm doing it. So I'm going to stop this share and I'll share the class schedule. Okay, so here's the class schedule, and let me talk a little bit about Let me talk a little bit about where we're at and where we're headed. So, you know, we were on schedule. Everything was following the pattern. And then, if you recall, I decided to sort of call a little bit of an audible. And we were going to cover structural analysis, method of joints and method of sections. But I decided I think it'd be a better idea to go ahead and cover centroids first. Centroids can sort of affect shear and moment diagrams. It's something that you can navigate, but I figured let's go ahead and do the centroids part first, just so that we don't have to cover that as well. And as a result, we're a little bit off the original schedule, and I thought, well, how can I arrange the next I guess couple of weeks in a way that goes along with that. So here's what I decided to do. Need to close that. Hold on. So and hopefully everybody's okay with this. So today we're covering our last discussion of centroids. I do have a topic that I want to cover. It's actually wasn't listed on the schedule, but because we're covering centroids, the concept of moments of inertia is such a natural extension of that I decided I want to throw that in the mix a little bit. It's not hard, but it's an incredibly important concept to understand. So we're going to cover moments of inertia. We're actually going to start it a little bit today, and then on Monday we're going to have like a full-blown example of that, and then we're going to get into structural analysis, and we're basically going to cover structural analysis from now until the third exam. Let's talk a little bit about that third exam. I think what I'm going to do on the third exam is I'm going to put trusses, shear and moment diagrams, and then centroids. That's actually a really good collection of topics. And as for when I want to do it, this is what I decided. I think I want to do that the week before Thanksgiving. That way we've got a little bit more time to put some stuff on there. We'll cover, we'll do our exam review on Monday. We'll do our exam on Wednesday, and then to give you all a little bit of a break, we'll go ahead and cancel class on Friday because we're making really good progress in here. And I thought it's the day before Thanksgiving. You all have been a really good group. You've been troopers throughout all of this. We'll go ahead and cancel class on Friday. Does this schedule work out for anybody? Is there anybody that like any major exams or anything that I'm not aware of? Because we can tweak this a little bit if needed. I figure it's more than enough advance notice that you all can plan around it. Any questions about this? Okay, good. So that's what we'll do. We'll have our third exam on the week before Thanksgiving break, and then what I'm going to do for Dead Week is we're going to spend Monday and Wednesday covering friction, because I think that's going to be our last topic of the semester. I do want to give friction the respect it deserves, but I also want to cover moments of inertia. So I thought that was a healthy compromise. And then Friday of Dead Week, we're going to have our review for the final. So with that, let me go ahead and just jump right into what we're talking about today. Today, we're basically gonna put a pin on centroids by introducing the idea of computing the centroid of a three-dimensional body, or a center of gravity of a three-dimensional body. And there's nothing here that you probably couldn't figure out on your own based on what we've already done in here. It's not like it's anything that's terribly complicated. If you can compute the centroid of a region, a two-dimensional area, you know, you're basically looking at this right here, the sum of AX divided by the sum of A, or the sum of AY divided by the sum of A. And if you could compute the center of gravity of a line, the sum of XL divided by the sum of L, then I think you could probably figure out where this is going for a three-dimensional body. And I think we actually mentioned that a little bit in class on Wednesday. I do want to briefly mention again the centroid references. Now, one thing I'll say about these is, you might think to yourself, well, these centroid references are for two-dimensional regions, they're for areas, so they're not very useful for 3D bodies. That's actually not the case. In fact, in practical engineering applications, these are pretty useful, not just for 2D, but for 3D as well. And I think you'll see what I mean as we jump into this. So let's talk a little bit about 3D. So how are we going to do 3D centers of gravities? Well, if the centroid of a line or curve you're integrating or summing with respect to distance, with respect to length. For centroids, you're integrating or summing with respect to area. For 3D bodies, it's with respect to volume. So I think that's probably a pretty easy concept to understand. If I wanted to find X bar, it'd be sum of X times the volumes divided by the sum of the volumes, and Y bar. And because we're in 3 dimensions, a centroid is going to have 3 coordinates. So there's also a Z bar. There's the sum of the volumes times Z divided by the sum of the volumes. Likewise, we can express that in terms of gravity, in terms of weight, and we can also represent that just in terms of the region of the volume. The difference being is that, what would the difference between the center of gravity be and the centroid be? It would be that if you were dealing with a 3-dimensional body that had different densities, like for instance, if you were trying to find the center of gravity of a car, the term center of gravity makes a lot more sense than a centroid, because a car is made of, there's the metal that goes into the engine, the aluminum, the steel. There's the rubber that makes the tires. There's all sorts of different materials. So a centroid it's not really very descriptive, because each of those different materials are going to have different densities, different unit weights, etc. So the center of gravity really makes the most sense, and that's why we would express that in terms of weight. In dealing in 3 dimensions, admittedly, I'd say center of gravity is probably the term that's used the most. Now, if you open your textbook, there is going to be a 3D centroid reference in there as well. I'll go ahead and tell you, I'm looking here at the book. It's on, in case anybody's interested, I'm on page 276. And again, this isn't exhaustive. In fact, I'm looking here at the one in the book, and there's 5 different regions. There's a hemisphere, a semi-ellipsoid, a paraboloid, a cone, a pyramid. I only have like 2 on here just because I couldn't really fit them on the slide, so they'd be eligible. Again, this is another one of those things you can find, more info in the textbook and an FE reference manual, what have you. Now, the problem that I'm about to do, actually, none of these shapes are in there, and you'll see why, because just because the shape isn't listed in a centroid table doesn't mean you can't find the centroid very, very easily. One other point I will mention before we get into the example here in a bit is the concept. If you open the textbook, you're going to see some problems in the book that are a little bit more calculus based. For example, if I have some irregular shape, what is the volume of that shape? And usually it involves, here's the shape, we define the shape, and then we do an integral. A lot of times you'll do that integral, for instance, in polar coordinates. You'll define the curve and then integrate it around the circle, or maybe something like a theorem of Pappus or whatnot. I'm choosing not to cover that in here, not because it's not important, because it is important. But if I was a betting man, you're probably going to be doing that anyways in a Calculus 1 or a Calculus 3 class or something like that. And so I just want to kind of cover the stuff that I think is really applicable to engineers that you're not going to get in another course. So I'm going to leave that there. What I want to do is something that's a bit more applicable to engineers. So I want to compute the centroid of this. And I'll go ahead and tell you that I'm probably not going to do the full X, Y, and Z coordinates. Like, I'm probably going to pick one axis and just do the centroid with respect to one axis. And I think you'll see as we're going about this, it's not that it gets harder. after a while, the point's made, and it's like, let's spend our time doing something else. So we're going to compute the location of this sort of machine part shown. If you look at the part, you can see that each of the plates or the components are 1/2 inch thick. So that's something to keep in mind. Each of those two holes are 1 inch thick. Another thing that I do want to point out is that if you open your textbook and go to, this Centroid reference, you're really not going to find any of these shapes that you in this Centroid reference that are represented in this problem. But as you're going to see, I don't think we need a Centroid reference to determine some of the individual centroids of these components. Like, for instance, I'm looking at this shape, and I'm seeing for instance, let me use like red here. I'm seeing, one region here that just sort of looks like a box to me. And I don't know about you, but finding the centroid of a box is a pretty simple prospect in my opinion. So I don't need a table to look that up. And so a lot of times you won't have a centroid reference that has the values there, but I don't think that's very difficult. Before we jump into the problem, there is one thing I do want to make sure that you watch out for. I'd say probably the hardest thing, at least in my experience, that has been with computing centroids of three-dimensional shapes like this, is to make sure that you don't overlap your regions and don't double count different components of the part. But that'll become clear as we jump into the problem. Let me stop the share here. Share the screen, which, by the way, if there's anybody that's having any connectivity issues, let me know. We were doing I had structural analysis at 10, and there were I had structural analysis at 10, and there was some students that were having some connectivity issues, and it wasn't one student, a number of students. So if there's any issues there, let me know. Okay, so here's the problem that we're doing. Let me put my keyboard over there to make this a little easier. I'm using a little bit of a different version of OneNote that I think is going to be a little easier and going to result in a little bit less jumping back and forth. Okay, so here's the part. First thing we're going to do is we're going to adopt the same strategy that we have in previous problems, and that's to split this up into simple components. Okay, so here's how I'm going to go about this. And to be clear, I don't think there's any real right way or wrong way to do this, just as long as you don't double count your areas. So the first shape that I'm going to do is I'm going to say that we've got this rectangular block. Now here's the thing though, when I draw this rectangular block, I'm going to say that this rectangular block incorporates this region here. Okay, so it's going to incorporate that little back component there as well. The second component, this part here, we're going to take each component here one at a time and see if we can define it. So my second component is going to be that little semicircular wedge that you see right there. The big thing right here is to make sure that you're not double counting that area, because see how the two regions loop over? So like if I draw this from up top, so here's this. My blue shape, the blue shape I'm saying extends all the way over here, and then the green shape sort of goes like that. So just to make sure that you don't define the green shape to go all the way over here, because then you'd be double counting that area. I hope that makes sense. If anybody has any questions about that, let me know. The third region that we're going to define is, well, we have two of them. We have these circular holes. So just like before, I'll sort of do that. Just like before, we're going to treat those not as negative areas, but as negative volumes. Okay, and so let's see if we can take each one of these parts one at a time, and let's see if we can define a couple of things about them. So let's start off. I'm going to erase this if that's okay. Let's start off with, I'll call shape number 1. And let's see, maybe let's come up with a name for this. Let's call it the rectangular prism. So what I mean by that rectangular prism is I'm talking about this blue shape, the blue rectangular one. And so first thing we probably need to compute is the volume. Does anybody help me out? Does anybody know what the volume of that that blue block is? So we're talking about basically this part here. We're just talking about that part right there. What's the volume of that? Okay, so you got 4.5 cubic inches. And so maybe what we'll do is we'll say, okay, this is 4.5, right? This is, we've got the thickness here, and the thickness is a half an inch. But the issue becomes, okay, what's that dimension? That's probably the one that's kind of hard to see. And the easiest way to find that is to look at the semicircular region, right? Because the semicircular region has a radius of 2 inches, which means that this is 2 inches as well. So the volume is 4.5 times 2 inches times a half an inch. So the volume is 4.5 cubic inches. Okay, so that was exactly right. Exactly right. Okay. And so the next thing that we probably need to see if we can figure out is what are the x, y, and z coordinates of the centroid. And so let's see if we can write the x, y, and z. Okay, so let's take the x-axis. How far along the x-axis will we travel in order to get to the centroid of this region? And so remember, x-axis, we're talking about that one right there. There we go, 1/4 of an inch. Exactly right. What about the y-axis? Now, Miss, yeah, I'm glad we had that in the chat. So, so we had people saying -1 inches because you're going down in the z axis or in the y axis. So make sure that you keep track of your signs. Remember, positive axis goes up. So yeah, that's -1. That's an easy thing to mess up on a homework or on an exam. Along the z axis, what's that going to be? All right, 2.25. Exactly right. Yeah, just half the 4.5. Okay, exactly right. Okay, there we go. Good. Okay, so now let's see if we can keep trucking. Now I might so I don't have to keep scrolling back and forth. Let's copy and paste. I'm cheating here. So now we're going to look at shape 2. And so shape 2 was that component there. So shape 2, we'll call this the semicircular region, or no, it's not a semicircle. It's I think I've been saying semicircle a lot. It's a quarter circular region. Okay, so see if I can redraw that. So it goes like that, like that, like that, like that, like that. That's about the best you're going to get out of me in 3 dimensions. So bear with me on that. Okay. This is a, okay, what pen did I pick there? Let's go ahead and use it. What the heck? All right, so this is a 2-inch radius. Okay, so let's start off with the volume. Okay, so somebody help me out. Can somebody compute the volume of this region? And maybe another thing I should add, this dimension here is still a thickness of a half inch. Maybe I'll use my little Galaxy pen for that so that it shows up a little more clearly. All right, so what are we getting for a volume there? I'll do it with you. Anybody have an answer for me? And so let me, if you're working this out, you're like, well, how do you compute the volume of this? Maybe one way of looking at it is the area times the thickness, right? Because basically all this is a region that's a half inch thick. And what is the area of that region, right? The area of that region is going to be, well, it's a quarter circle, right? So the area of a quarter circle is pi r squared over 4 times the thickness. So it's going to be pi over 4 times 2 inches squared times a half inch. Because again, basically what we've got is we've got a quarter circle that has a thickness of half inch. And so what you should get is something like 1.571 inches. No, not it. Nope, sorry, that's wrong. Inches cubed. All right, I want to hold off on that and see if there's any questions. If that's confusing or whatnot, because that's kind of important. Oh, goodness. My coffee maker's going nuts. Everybody good? Now, let's look at centroids. Okay, so now let's look at X, Y, and Z. Okay, now I'm gonna do this in a little bit of a different order. Let's do Z first. Does anybody know what the centroid's going to be along the Z axis? While you're doing that, I'm going to see if I can find something. It's going to be a quarter of an inch. Okay. Now, what about the, which one do I want to do? Let's do the y-axis. So let's put some coordinates here on my little image. So what I've got here, I've got basically that, what is this? I've got that this is the x-axis. I've got that the y-axis goes like that, and the z-axis goes like this. So if I have this region, and that, let's say that's the centroid, what I'm looking for is that distance right there. Does anybody know what that's going to be for a semicircular region? Anybody know how you compute it? While I'm doing that, I want to see if I can pull something up. Anybody got an answer for that? Try that. I'm going to stop the share real quick. Share files. Let's share a little bit of an older set of lecture notes. Let's go to lecture 27 once this uploads, because I want to show you something. Okay, so these were the Centroid references from lecture 27. And what I'm specifically focused on right now is this right here, because I'm basically trying to find the X and Y centroid of that. And what this is saying is that from the corner, the centroid is going to be defined as basically this term here, 4r over 3 pi. And it really doesn't matter what direction I go. So if I go back to my notes here. Okay. If I go back to my notes, I propose that this distance here is 4r over 3 pi. So my y centroid is going to be, and let me see if I can move some stuff down here. It's going to be 4r over 3 pi, but it's going to be negative because along the y-axis I'm going down. So I think Mr. Maybe Mr. Paycheck might have been what you were looking at there. Minus 8 divided by 3 times pi. 0.849, but negative. So maybe I'll space that out a little bit so it's a little easier to read. All right, does that make sense? Is everybody okay with that? All right. Okay. No, that's no worries, no worries. Okay, now for the x direction. Now for the x-axis, here's the thing about the x-axis. Let's see if y'all are paying attention. If we got 0.849, what is the centroid with respect to the x-axis? So it's 0.849 for the y. Okay, so I'm seeing some 849s, right? Here's the thing. No, that is not correct. And here's why. Where is the origin? The origin is right here, right? That's the origin. So along the x-axis, how do you go from the origin to the centroid, right? Well, here's the centroid, right? So we're basically trying to find this distance right there. And so it's not 0.849, it's 0.849 plus half an inch. You got to account for that other half an inch because the origin is actually, the origin's actually like over here. There's an extra half an inch we got to account for. So yeah, this is probably the hardest part, is just like the bookkeeping. So it's half an inch plus 4r over 3 pi. And so it's 1.349. Does that make sense? Does that make sense? You got to account for that little bit on the end. Good. Yeah. This is the stuff I want to make sure that we're comfortable with. Okay. So again, I'm going to cheat a little bit. I'm going to scroll down. Who is calling me? They can wait. Now, unfortunately, I can't really close Teams because I'm using this notebook here. So I guess I could, but I don't want anything to not sync. So I'm just sort of going with it. The downside of leaving Teams up, stuff like that. My apologies. Okay, so now let's look at these circular regions. I'm going to kind of handle them together because they're both the same volume. So 3 and 4 circular holes. Okay, so they both have the same volume, okay? And the volume, this is just a cylinder, right? And so how do you determine the volume of a cylinder? You take pi r squared times h, okay? So, but now hold on. I'm doing something wrong here because its volume equals negative pi r squared times h. And why is the volume negative? because it's a hole. We're removing that material from the part. So it's negative pi r squared is r, the radius. What is the radius of these? What the problem said? The problem said these were, so the diameter is 1 inch. So the radius is ½ inch. And so ½ inch squared times the height. The height, that's the thickness, and the thickness is ½ inch. And so that's basically pi over 8, I believe. Yep. And that is negative. I'm getting 393. 393. Okay. And then now all we have to do is locate the x and y coordinates of the center. So maybe I'll have x3, y3, z3. And then I'll have x4, y4, and z4. And let's just fill it up. So we'll start off with the third one. And so let's see, maybe we got to come up with some names. Let's call this 3. Let's call that 4. Okay. So for the third one, first off, along the x-axis, they're both 1/4 inch. Right? Because they're both in the same direction there. Along the y-axis, they're also both the same. And I think that's -1. What changes is the z-axis, because the two holes are separated by a distance along the z. Somebody help me out. What is z3? Z3 is 1. Well, hold on. Now here, yeah, check this out. Okay, that 1 is right there, and so that's right there, right? So really what you want is that dimension. So it's not 1, it's 1.5. I know that's an easy one to mess up. Yeah, that's 1.5. So if this is 1.5, somebody tell me what Z4 is. 3.5. There we go. Exactly. There you go. See, it's not hard. It's just this little nitpicky bookkeeping that can happen sometimes. All right. Is everybody okay with this so far? Okay. All right. In the interest of time, I'm not going to do all of these. I'm only going to do one, and I'm going to let you all pick. Somebody help me out. X, Y, or Z. So we'll maybe this is like Twitch chat, and I'm asking chat like who's the imposter. Dr. Mike's looking kind of sus or something. Okay, let's go with. I got a lot of people saying Z, so we'll do Z. Okay. So all right. So let's do shape. Z's kind of sus. All right, so we had 4 shapes. All right, and so this is set up just like anything else that we would do. We would write the volumes. We would write the individual Z's. And then we'd write the VZs, like we would multiply each row. All right, so I'm going to cheat a little bit. Okay, so let's see what I can write out. Okay, so this is 1.5, this is 3.5. So if you can see what I'm doing now, I'm just going through and filling in the table with all the data that we know. So this is negative 0.393, negative 0.393. So remember, those volumes are negative because those are the holes, and then I got the Z's from here and here. So I'm just going through and writing down everything. So let me scroll up to 2. 2 was 1/4 inch and 1.571. So 1.571 and we'll say 0.25. Yeah. And then this volume here, that was 4.5. And let's see, hold on. 4.5, and this is 2.25, right? So 4.5 and 2.25. Okay, so that's just me going in and filling in all that stuff. And then at this point, it just becomes kind of rote, okay? So we just take each row, so 4.5 times 2.25. This is going to be 10.125, right? So next I've got 1.571 times 0.25. I'm getting 0.393 here. And then this one times 1.5 negative 0.589. And then this one times 3.5, getting negative 1.37. I'm getting 374. And so then we start summing these up. And so I'm going to sum up, you know, the volumes and then the volumes times the Z's. So let's do the volumes times the Z's first because I got that in my calculator history right here. Okay, I'm getting 8.554. And then let's see, this one. This one. I'm getting 5.285. So therefore, the Z bar is going to be the sum of the V times the Z's over the sum of the V's, which is 8.554. And that's inches to the fourth because you take an inches cubed times an inches divided by 5.285 inches cubed. And so you get 1.618 inches. So Z bar 1.618 inches. Okay, so what do you think? Any questions on that? I mean, like I said, we just did the Z-axis. If I did the X-axis and the Y-axis, I would just be more. I just do the same thing for the X, the same thing for the Y, and I just, you know, same process. Again, the hard part is that overlapping, and whenever you have a segment that's over, like, you know, when we were determining the centroids, like, oh, you got to add that 1/2 inch, or you got to add that one segment. Maybe I should have worn like an orange hoodie and like ski goggles, and then, I don't know, tape like a leaf to the back of my head or something. You know, the Among Us. I don't know. I'm a dork. It's okay. Everybody good? Okay. We've got 10 minutes left, and I want to introduce this topic called a moment of inertia because this has some very, very real connotations to engineering, and it's such a natural topic to discuss now that we're talking about centroids. And I'm going to keep it kind of basic in here, but I do think it's really important. Let me go back to files. Okay. So I want to go back to basics with how we defined this stuff. So let's talk about moments of area. So if you remember, one of the first problems that we did was where we derived the properties for a given region. Like, remember, we had a problem that was kind of like this, and we said, okay, compute the area and compute the centroid of that region. And in order to do that, we introduced this term called a moment of area. So, remember, we had written things out. We said, okay, if you integrate, if you integrate the dA term, that's going to give you the area, because you're basically summing up all those little rectangles. But if you integrate the x times dA, that's going to give you the first moment, because basically what you're doing is you're saying, here's these little rectangles, right? Multiply them by a moment arm, and then just sum them up. And we call it a first moment of area because we only multiply it by that distance once, okay? Well, what if we did it twice? What if we said, okay, what if we multiply, instead by x, we multiply by x squared, okay? That would be what's called the second moment of area, okay? And the second moment of area is very, very important in the world of engineering. We have a special name for that, that second moment of area, and we call it a moment of inertia, okay? Moments of inertia have a very, very profound impact on structural response. And I'm going to give you a very basic real-world example of that. So I'm curious if anybody in the class has ever done any sort of framing or any sort of building, if you worked on anything around the house, even if you haven't. I'm going to give you a really, really basic example. So I have here in my hand, I have a little, it's actually a little slide rule. This was my grandmother's slide rule when she was in college, so it was pretty slick. Now, you could do this, if anybody here has a ruler or a yardstick or anybody around, you can do the same thing. And I'm sure you've probably done this before and never really thought about it. So let's say I've got this little, ruler type thing. What you'll find is, for an object like this, it's a lot more flimsy, sort of, if I bend it this way than if I bend it this way. It's really, really tough to bend this thing, this way than it is that way. And up until now, I mean, yeah, you can physically see that it's stiffer this way than it is this way, but why? Why is it stiffer one way than it is another? Or is there a numerical way that we can compute that? Or can we identify that? And the answer is yes. The way that we can express that is through what's called the moment of inertia. Okay, so like, for instance, if you're framing out like a deck in your backyard or something, there is a reason why you take the floor beams and you stick them vertically as opposed to horizontally. The reason why is because along that orientation, they have a larger moment of inertia. Okay, the formula that we use for the moment of inertia, and we're going to sort of develop that here in a bit, but to give you some really basic understanding, the moment of inertia of a rectangle about its centroid is bh cubed over 12. What you find is, if you look at the orientation here, so let's say you've got a rectangle, right? We call this side B and this side H. The moment of inertia is bh cubed over 12. Well, just think about the way they're oriented. This beam is going to have a higher moment of inertia than this beam, because the height is higher for this one than it is for this one, okay? And so if you take a rectangle, just draw any rectangle and compute the moment of inertia if it's oriented one way or if it's oriented another, and you'll see that the moment of inertia is much higher when the rectangle is oriented this way. That's why when you erect, like, joists for a deck in your backyard, you're going to face the beam so they're facing upward, because you have a higher moment of inertia. The moment of inertia, no, that's a great question. So it's I equals B times H cubed over 12. The H is cubed, but not the B. Great question. So because it's got that cubic term with respect to the height, you want to orient the height the way it's being bent, so you're going to get the higher orientation in that fashion. You can compute a moment of inertia actually really easily through an integral, but I'm going to show you an algorithm that we're going to use on Monday. It's called the parallel axis theorem, where you can use a lot of these references that you see or that we've used before, and you can use that to determine the moment of inertia of an arbitrary shape. It's like, we'll probably do it for something like an I-beam, and you'll see how it works. Let me go to the notes here, because this is a really quick problem, and I think this is kind of valuable. So I want to go back to this problem here. I need to share the screen. That would help. I've got my thing pulled up, and I was just going to get ready to start talking, and class was like, what are you talking about? We can't see anything. Okay. So I want to go back to this problem. We've already computed a lot of the properties for this problem. If you remember, we had the area was the integral of dA, and we did that as saying the integral from 0 to 3 of x squared, right? And then we had a first moment of inertia or first moment of area. So for instance, we had qy, and the first moment of area was the integral of x dA, or integral of x dA. So we integrated 0 to 3. Instead of x squared, it's just x to the third. Well, you could see where this is going. If I want to find the moment of inertia about the y-axis, I'm going to take the integral of x squared dA. So it's not harder, it's just more. And so, what am I going to get? I'm going to get the integral from 0 to 3 of, what is that? X to the fourth dx. So, what is the integral of x to the fourth? It's x to the fifth over 5, right? From 0 to 3. And so plug in the top number minus plug in the bottom number, and, you can evaluate that out. So ultimately, what you get is 243 over 5, or what do we get when we check that out? That ends up being like 48.6. Okay. Now, if you compare that to the moment of inertia about the x-axis, well, how are we going to do that? Well, maybe I should rewind a bit. So we had done a qx, right? And that was the integral of y dA. And if you remember, the way that we had to do that is we said integral of y times, what was it? It was 3 minus the square root of y dA. Remember that? Because we had to integrate with respect to dy. And we did that from 0 to 9. So that was the integral from 0 to 9 of 3y minus y to the, what was that, 3 halves? Right? Well, we're going to do the same thing here. It's just going to be another y term. So the moment of inertia with respect to the x-axis, instead of the integral of y, it's going to be the integral of y squared. So integral from 0 to 9 of y squared. Don't worry, this isn't on your homework. I'm just going through this just so that we have some reference here. So let me just chug this out. So this ends up being 729 over 7, or Ix is 104.14. And so if you compare this number to this number, you can see that the shape is clearly stiffer in one direction than it is in another. And you see that when you just exactly correct, but it's pretty close. But the shape is much taller then it is wide. It's definitely a shape that's, you know, sort of longer in one direction than it is in another. So it makes sense that the moment of inertia about the x-axis is higher than the moment of inertia about the y-axis. Now, what I'm drawing here sort of presents a little bit of a problem. I'm drawing these axes with respect to the centroid. These axes down here are with respect to, you know, just the origin. How do I translate that, and how do I get a value that's usable for later courses? That's the parallel axis theorem, and that's what we're going to talk about on Monday. But any questions, though, before I call it? I know I rushed through the calculus really quickly, but I'm not worried about you all doing this calculus on a homework assignment. I'm not going to test you on that. I just want to present it from a concept standpoint. Any questions? All right. Well, everybody, stay safe, stay healthy. Happy Halloween. We will see you all on Monday. You all have a wonderful weekend. Everybody have a great weekend.